Hi, Chem 151 students, and welcome back for week 13. So for week 13, I'm going to be starting to tell you about thermodynamics, and this is not going to be on the next exam, but it is related to some of the concepts in your experiments that you were starting on last week and finishing up this week, experiment 15 and 16. So for these experiments, they talk a little bit about entropy and free energy. So I wanted to at least introduce the concepts, even though they're not going to be on the exam. The focus of this week is really going to be practice, additional practice. I feel like that always helps with this kind of material. And so although we don't have a lot of any new material that's coming up on the next exam, I do think that it's important that you get some practice on that, some additional practice. And so I'll be focusing the homework problems this week on continuing to practice what it is that we're going to be getting ready for the exam, but I did want to kind of give you an introduction to thermodynamics. And so we're going to start with the topic of entropy, a very interesting topic actually, and it's going to get into why certain chemical reactions and physical processes occur on their own. And so this is a really interesting idea, and this is going to be related to another idea called free energy. Both of those are discussed in your labs this week. So I wanted to give you a brief introduction to these. Even though you could probably complete the labs without knowing about them just yet, it does give it a little bit more context. So we'll start by talking about what is a spontaneous process. A spontaneous process is one that will proceed on its own without having to make it happen. And so there's certain things we make happen, like, if you want to cook something, you put in energy, right? Or if you want to boil water, you heat it up and you make sure that happens. It won't happen on its own. An example down here is one of spontaneous process. As we go from left to right, we've got a flask full of gases here. You could think of this your tire full of high pressure gas. And then you open the valve here, and then once it's open, the gas can flow freely from the left flask to the right flask, and it will spontaneously flow until the pressures in both flasks are equalized, and that is a spontaneous process. The reverse, going from these two flasks and then suddenly having an empty flask on one side and a full flask on the other while they're still open, is something that you really wouldn't expect to happen. So we always have a sense for what's spontaneous and what isn't. But what is it that makes a process spontaneous, and how could we predict whether a process will be spontaneous or not? That's something that we're going to be focusing on a lot in this chapter. So another example of a spontaneous process is the rusting of these tire rims here, as you can see. Now, notice that the process that I showed you before, that would probably happen relatively quickly. But the rusting of the tires, that happens relatively slowly. But both are spontaneous. And that is because we're talking about something different than what we talked about back in chapter 16, having to do with kinetics. This is a completely different matter that we're talking about. In terms of an energy diagram, we can explain it in this way. So back in chapter 16, we made energy diagrams, and this is an energy diagram for an exothermic reaction. The reactants are higher in potential energy than the products, and so this reaction will go from reactants to products, but whether it's fast or not depends all on the size of the activation energy. If the activation energy is high, a spontaneous reaction will occur, but it will occur more slowly because there will be few reactant particles that at any one time have enough energy to overcome this transition state energy barrier and make the products. If the activation energy is small, then the reaction will go more quickly. But what we're not focusing on the size of this activation energy here. That all has to do with kinetics. What we're focusing on is the relative energies of reactants and products and other properties of those. Those are wrapped up in this quantity right here, the difference in energy between the reactants and products. And in the past, we've thought about this as heat energy or enthalpy, but we're going to be thinking of a different kind of energy as we move forward called Gibbs free energy, which gives us a better indication of whether a reaction will be spontaneous or not. But what we're not going to be concerned with is activation energy. We're not talking here about how quickly or slowly reactions happen, only whether or not they will happen if given enough time. So some of the properties that we've been discussing can be described as what are called state functions. And this distinction between state function and not state function becomes very important when we're talking about the spontaneity of these reactions. A state function is a function whose property only depends on the present state of the matter and not the way in which the matter arrived at that state. Generally, state functions are indicated in notation with a capital letter. So for example, enthalpy or heat energy. This is a state function, which is, you can tell because it's the capital H. And so enthalpy is defined as the heat change at constant pressure. It can also be defined as with this equation here, delta H equals delta E plus P delta V. Now, entropy is a different state function. This is a measurement of the amount of molecular randomness in a system. There are actually various ways in which entropy can be described. This is one definition. If you go into the Wikipedia article on entropy, they'll probably give you a few more. But a really good way of thinking of entropy is just how random the particles in the system are and how much freedom they have to move around and move into new configurations. So to differentiate between a state function and a non-state function. So here we have a set of reactants here, which is gasoline and oxygen with a certain energy to them, a certain potential energy. And those reactants can be burned to produce CO2 and water. But what happens when you burn them depends on the way in which you burn them. If you burn this gasoline in a barrel like this, all of this energy will be given off as heat energy here. However, if you burn the gasoline in your car engine, some will be lost as heat, but some of that energy will be used as work to move your car. And so work and heat are examples of non-state functions here. How much work or heat you get out of burning this substance depends on the way in which it is burned. However, the potential energy of the reactants and the products is the same regardless. It doesn't matter if you burn it in a barrel or in a car engine. The energy difference between the products and the reactants is the same. But whether that energy is released as work or heat depends on the way in which it's burned. So work and heat are not state functions, but this enthalpy and this potential energy are state functions. Now, when it comes to thinking about whether a reaction is spontaneous or not spontaneous, often you'll think that there are reactions, for example, like something burning, like this methane burning here. This is an exothermic reaction. It releases energy. And lots of exothermic reactions happen to be spontaneous. There is a reason for that. But there are other endothermic reactions that are also spontaneous. For example, if you leave a block of ice, solid water, out on the counter, this will spontaneously turn into a liquid, even though this requires energy. However, another endothermic process, liquid turning to gas, this will happen spontaneously to some extent, but if you want it, generally energy has to be put in. It's not really spontaneous, liquid water turning to a gas at room temperature anyway. Another example of an endothermic reaction, or a reaction that has a positive delta H, that's how we quantitatively identify an endothermic reaction, would be this N2O4 gas making two NO2 molecules. This is a process that is also spontaneous, even though it's endothermic. So why is that? It kind of makes sense if you're thinking about like the energy of a molecule, like a ball rolling down a hill. So we have these energy diagrams here, and I kind of have told you in the past to think of it like a ball rolling down a hill. If it's an exothermic reaction, you might expect, oh yeah, if this ball can get over this hill, it will roll down and make these products. So if these molecules can get enough energy to start the reaction, they will definitely go ahead and go to that lower energy state. But then again, some endothermic reactions are also spontaneous. So what's going on there? Another example is the solubility of sodium chloride, also endothermic, but spontaneous as well. So what is driving these reactions? If it isn't as simple as any reaction that releases energy is spontaneous, what is spontaneous here? It's obviously not all exothermic reactions, and some endothermic reactions can be spontaneous. So we're going to need a more nuanced view of figuring out what makes a reaction spontaneous or not. The answer is going to lie in the concept of entropy. It's going to be related to not only the concept of being exothermic or endothermic, but also to this idea of entropy. So entropy is indicated with a capital S, and the change of entropy in a reaction is indicated by delta S, delta meaning change. And so S again is a measurement of the randomness, the freedom of motion of molecules. And so we can see here, for example, that if molecules or particles are in a solid, they have a lot less freedom of motion than if they're in a liquid. Now these particles can roll around one another and pass by one another, and they're not stuck rigid in a very orderly formation like when they're in a solid. And then if you have molecules in the gas phase, these have much more freedom of movement. They don't even have to be next to each other. They can fly all around the place here. And so melting a substance results in an increase in entropy, and then vaporizing a liquid to a gas is another increase in entropy. In fact, it's a much greater increase in entropy. These gas molecules have a much greater freedom than do the liquid molecules here. And then the opposite way, condensing from a gas to a liquid involves a loss of entropy. From a liquid to a solid is also a loss of entropy. So in general, gases have much more entropy than liquids, which have somewhat more entropy than solids. By far, the greatest entropy is gases. So that's one thing to keep in mind. So gases have greater entropy. In terms of the number of molecules here, so if you have more pieces, more molecules, there are more ways in which they can arrange themselves, particularly if those molecules are gas molecules. So in the example of N2O4, producing 2 molecules of NO2, we have twice as many molecules once this reaction happens. And so those molecules have much greater ways of arranging themselves because there's more of them. So when you have a reaction that increases the number of molecules or particles, particularly if those are gas molecules or gas particles, then you will have an increase in entropy. And the opposite is true too. So if you have fewer number of gas molecules, you'll have less entropy. Finally, for the sodium chloride example here, and for the for any ionic compound or anything, when you dissolve something in water, you mix things in some way. So especially a solid like this sodium chloride is very, very orderly, not much randomness at all. However, when you dissolve the sodium chloride in water, it splits up into individual ions, and now those ions they have a lot more freedom to move around, and so they can be much more random orientations. Now, it's not completely random. You can notice there's some orderliness here too, in the fact that the water molecules solvate these ions, and the positive hydrogen side of the water molecule is attracted to the negative ions. The negative oxygen side of the molecule is attracted to the positive ions. However, you can see that there's a lot more possibilities for the movement of these ions than there was when it was a solid. So generally, mixing things in some way it results in a greater entropy, particularly if you have something that's a very organized solid like this dissolving and creating smaller particles. So how can we quantitate this idea here? There is a way to quantitate the idea of how orderly something is, and it's based on the number of possible arrangements that molecules or whatever is making up this matter can take. Now, this is something that's very difficult to actually quantitatively say for molecules. There's lots of different orientations they can be in. They can flip around and spin around in different ways. They can be closer or farther. So it's a lot easier to describe entropy for like a binary system, like a coin flip, like this one here. So a great way to think about entropy is in terms of probabilities here. So the example I always like to use is a deck of cards. So you take a deck of cards. When you first take it out of the box, you'll notice that it's arranged very orderly from ace to king, and then suit by suit, and there's this one arrangement of it. Then when you start to shuffle it, what do you think of the chances that it's going to go back to that original arrangement that it came out of the box in? Very unlikely. You're going to sit there and shuffle forever till it gets back, and for many, probably thousands and thousands of lifetimes until those cards get back into their original orientation that they came out of the box in. Another example here is with coin flips. So the randomness of a system depends basically on the number of different ways in which you could get that particular arrangement. So for the box of cards, there was only one way to get that arrangement that it came out of the box, but there's 52 factorial ways in which the cards could be arranged out when you shuffle them. And so that's only one out of many, many jillions, as a technical term, of ways that the cards could be arranged. Likewise, when it comes to a coin flip like this, there's only one way that you could get, if you flip the coin 20 times, 20 heads and 0 tails. It's that they all have to be heads, and so this is a perfectly orderly structure, all 20 heads. However, let's say you're talking about the arrangement 9 heads and 11 tails. There's lots of different ways in which you could get 9 heads and 11 tails. Maybe your first flip is heads. Maybe your first 9 flips are heads, and the next 11 flips are tails. That's one way. Or it could be heads, tails, heads, tails, heads. It could be lots of different possible arrangements that are or sequences of coin flips that could give you 9 heads and 11 tails in 20 coin flips. And so the way we can measure this for a coin flip like this with only 2 states, the number of possible arrangements, if we flip the coin 20 times, would be 2 to the 20th power. Because there are 2 possible arrangements and it's 20 flips. And so that's a lot of different possible arrangements. And only one of those is all heads. And only one of those is all tails, let's say. But there's lots and lots of them that are 9 heads and 11 tails. And so this is a much lower entropy type of arrangement than this 9 heads, 11 tails arrangement. And quantitatively speaking, if you want to define entropy, it would be this Boltzmann's constant, 1.38 times 10 to the minus 23 joules per Kelvin, times the natural log of the number of ways in which the state could be achieved. And so the entropy of this state, since there's only one way it can be achieved, this would be the Boltzmann constant times the natural log of 1, which would be 0. So this would be what a zero entropy arrangement looks like. Just basically perfectly ordered. Everything is perfect. Everything is perfectly heads here. But if we were looking at this arrangement, well, there's lots of different ways in which this could be achieved. So the entropy would be much higher. So this would be a much higher entropy. But you could calculate it exactly using this formula. Now, I don't generally have you use this formula exactly. I want you to understand the concept of entropy. And so this formula doesn't help that much in that regard, except to describe the way in which entropy is related to probabilities quantitatively. So you don't have to use this equation per se. I'm just using it kind of as an instructional tool. So related to that, so you saw with the coins, the perfectly ordered coin situation was 20 heads, all heads. And that was zero entropy. For a molecular substance, for matter, we're going to describe matter as having zero entropy if it's a perfectly ordered crystal at 0 degrees Kelvin. So Kelvin temperature is really important here. Kelvin temperature indicates zero molecular movement. So at higher temperature, molecules have a higher average kinetic energy. And so at higher temperature, you have greater molecular speeds. You have a broader distribution of individual kinetic energies. This is shown by this Boltzmann distribution right here. So most of them are all around this speed, but some of them are much faster, some of them are slower. At higher temperature, you have more movement of molecules, thus you have more randomness and higher entropy. At lower temperatures, you have lower average kinetic energy, so you can see that here the average is lower. A narrow distribution of individual kinetic energies. You have lower entropy overall, less motion for these molecules. And the idea here is that if you drop the temperature lower and lower and lower, if you finally get to the theoretical temperature of 0 Kelvin, that is zero molecular motion. And that's the only way that you can have exactly zero entropy. A perfectly ordered crystal structure with zero molecular motion. So unlike a very interesting difference between enthalpy and Gibbs free energy, which we're going to learn about, is that they don't have a zero value. They're all defined relative to the energies of other substances, but entropy does have a zero value. It's defined as the crystalline substance at 0 Kelvin. So there's never zero entropy at higher temperatures than 0 Kelvin. Entropy increases with temperature. So this is what we can see for a particular substance, all the same substance here, a pure substance that is having its temperature increased. So you guys know that once you get to the melting point or the boiling point, the substance has to undergo a phase change before it will increase in temperature. So you can see here, as we increase the temperature of a solid at 0 temperature in Kelvin, it is zero entropy. And as we increase the temperature, the substance remains solid, but its entropy is increasing and increasing until it gets to the melting point. And at that point, all of the energy that you add goes into disrupting the entropy of the substance and turning it from a solid to a liquid. So entropy rises while temperature does not. Then the substance becomes completely liquid, and as you raise the temperature of the liquid, the entropy is slowly increasing. Then you get to the temperature that is the boiling point. And then the entropy jumps up again. All the energy that you're putting in is being turned into randomized, giving these molecules greater molecular freedom, breaking them apart from one another so that they exist in the gas phase. And then as you increase the temperature of the gas further, the entropy increases and increases with greater temperature. So take-home message here is entropy increases with temperature. And as we mentioned before, the entropy of a liquid is greater than the entropy of the solid. The entropy of a gas is generally much greater than that of the liquid. There's much more molecular freedom for a gas than there is for solids and liquids. So here's a table of standard molar entropies. So first of all, this idea of standard is going to become very important. Standard is indicated by this little degrees symbol here. So this is, when we say that standard entropy, it's the entropy of 1 mole of a pure substance at, and this is what standard means. Standard means 1 atmosphere pressure and a particular temperature, usually 25 degrees Celsius. But it's 1 mole, 1 atmosphere pressure. Concentrations are generally 1 molar. So that's what standard means. And you'll notice here that these are S standards. They have units of joules per mole Kelvin. Now, what I want to do is I'm going to be posting for you the appendix from the textbook that has this thermodynamic information. So let's go Chem 151 appendices. Okay, and so I've already posted for you Appendix C, which had all kinds of equilibrium constants. Appendix B has thermodynamic constants, and so you'll see there's going to be entropies, which are enthalpies, which you already know about. And there's going to be also entropies, and there's Gibbs free energy, which we'll talk about briefly before the end of this lecture. But notice the difference in these here. So enthalpy and Gibbs free energy all have deltas next to them. And for a element in its standard state, the enthalpy and the Gibbs free energy are going to be 0. And this is because if there's a delta, because enthalpies, and as we'll see, Gibbs free energies, there's no 0 except one that's defined. There's no 0 like entropy. Entropy has a 0. It's when you have a perfect crystalline solid at 0 Kelvin. But delta H's and delta G's are given relative to elements in their standard states. And so you can see for elements in their standard states, the enthalpy values are always 0, delta L, delta H of formation. And there's also a little F here. And we're going to talk about this formation. It's again because we have to define these relative to something else, whereas entropy doesn't have this F on the table, and it's not a delta because we define entropy relative to 0 entropy, and there is a 0 entropy. And notice none of these are going to have 0 entropy. Why? It's because you can only have 0 entropy at 0 Kelvin, but this temperature here, these temperatures are at 298 Kelvin. And so none of these entropies will be 0, even though enthalpies of formation and delta G's of formation can be 0. And we'll talk about that as we get to delta G in more detail later. But that's just a distinction there. You just see S standard. So the S standard also is given in terms of units of joules per Kelvin because it's dependent on temperature, as we'll see. Higher temperature is higher entropy, right? And so these are entropies. So one thing you're going to notice too is for gases, the entropies are generally quite high here. For liquids, they are lesser on average. And then for solids, they're low, especially for very, very orderly solids. Like diamond has a very orderly structure. Its standard entropy at 25 degrees Celsius is still very low. On average, solids have lower entropy than liquids than gases, although you can see there's some overlap. Water as a liquid has quite a low entropy because of its hydrogen bonding forces. So it has very strong intermolecular forces which attract one molecule to another, and that makes water quite an orderly liquid. And so in terms of liquids, water has a relatively low entropy. So you can use your knowledge of what entropy is to kind of predict what relative entropies there will be. Generally, again, gases the highest entropy on average, liquids lesser entropy solids, the least entropy, and also the stronger the intermolecular forces, the less the entropy will be, because the molecules will be very orderly. So water has strong intermolecular forces, causing those molecules to be quite orderly. And then, for example, carbon dioxide, its intermolecular forces are weaker than those of, say, ammonia. And so it has a slightly higher entropy there. Now, what are these tables for? So you guys used this table way in the past when you were calculating the delta H's for a reaction. And we can use these tables to calculate the delta S, the change in entropy for a reaction. And so this formula, as you can see, it's basically the same thing as you did in the past with delta H's. It's the sum of the entropy, standard entropy values for the products, entropy values of the products, multiplied by their coefficients in the balanced equation, minus the entropy values for the reactants multiplied by their coefficients in the balanced equation. So this is the same equation back in Chem 150 that you had for delta H's that you'd use the appendix for. Same equation here for S standards. That's why we have tables of standard entropies, so we can find the change in entropy for whatever reaction we might be interested in. So let's say, using standard molar entropies, we wanted to calculate the standard entropy change for this decomposition of N2O4. And so, as we had mentioned before, the entropy change here should be an increase in entropy, right? Because we're getting more gas molecules. So you should kind of be able to predict a little bit, whether the entropy is increasing or decreasing, at least based on things like, the number of gas molecules, whether something is being mixed or not, whether, you have more gases relative to solids and liquids, whether you have more molecules in general. Here we have 2 more molecules. All of these lead to greater possible, orientations and movements for molecules and possible ways in which they can be arranged. So for our delta S standard, it's going to be 2 times the S standard for the product here, NO2, minus the S standard for the reactant, N2O4. Okay. And so we go and look these up. So we can go back to the previous table here. We had their standard entropies right here, 240 for nitrogen dioxide, 304.3 for dinitrogen tetroxide. And one other thing too is you'll notice that bigger molecules have greater standard entropy because there's more possible orientations and movements of the atoms. So we can see that dinitrogen tetroxide has a greater standard entropy than NO2 just because it has more atoms in it, basically. Okay, so we're going to copy those, so they're right here. And so now we're going to find the delta S for this reaction. We're going to do 2 times the entropy of NO2, which is 240 joules per Kelvin per mole. We're going to do 2 times that since there's a 2 in the balanced equation, minus the reactants. We have 1 N2O4 times its S standard, which is 304.3 joules per Kelvin per mole. And this is where I'm going to talk a little bit about moles too, and moles and this particular all these energies and entropies and stuff. Often we can see the mole here would kind of cancel, so often mole is not written, but often it is. Because it's assumed if the mole isn't written, you understand per mole of reactant here, or per 2 moles of NO2. And so mole is sometimes written for these and sometimes isn't, and don't be alarmed by that. Sometimes the mole is just implied instead of written directly. So now we can calculate this here. So we've got 2 times 240 minus 1 times 304.3, and we get 175.7, and our units will be joules per Kelvin, or you can say joules per Kelvin per mole. Now it's written this way because you can see moles canceling, but really the mole is implied what it's saying here, what we're saying is that when 1 mole of N2O4 reacts, the change in entropy is positive 175.7 joules per Kelvin. Or when 2 moles of NO2 are produced, 175.7 joules per Kelvin is the change in entropy. The mole there is implied, so whether you write it or not, it's really the same thing. And I know that's something that's often confusing for students, especially when I'm telling you to focus on your units all of the time. This is one of those situations where sometimes the mole is implied, or here you cancel moles and then you still write moles. That is okay, because the mole here is indicating that per 1 mole of this that reacts, you have this entropy change. So we already covered the third law of thermodynamics. That was that zero entropy means a perfect solid at 0 Kelvin temperature. Let's talk about the 2 remaining laws of thermodynamics. In any process, whether it's spontaneous or non-spontaneous, the total energy of a system and its surroundings is constant. This is often called the law of conservation of energy. Now, this only applies to chemical reactions. It doesn't apply to nuclear reactions because E equals mc squared way back then. Energy and mass have some kind of equivalence. But for all chemical reactions, the energy of a system and its surroundings is constant. So if all this means is that if a reaction, for example, releases energy, then the surroundings is absorbing that energy. That's a law of conservation of energy. And the energy that comes out must be equal to the energy that goes in, or that was released rather. So if a certain amount of energy is released, for example, by like burning gasoline, as we saw before, then the surroundings must have gained that energy while the system lost it. So the system is basically your reaction or your closed container you're looking at, and the surroundings is everything else. And then also the second law of thermodynamics: in any spontaneous process, the total entropy of a system and its surroundings always increases. This is the important one. This is going to be what tells us what reactions are spontaneous and what reactions aren't. Spontaneous reactions are those in which entropy is increasing for both the system and the surroundings. This is often called the universe. In the universe, entropy is always increasing. It is increasing more and more and more, and molecules are getting more and more spread out, and eventually, when everything is all spread out and even, they call that the heat death of the universe. That is when the second law of thermodynamics has gone on and on and on until the entropy is at its maximum level. Then nothing will ever happen, because for things to happen, entropy must be increasing in the universe. And eventually that comes to an end. That's the end of the heat death of the universe. But in terms of the names of these, first, second, third law, I don't care if you know which one's the first or the second or the third. Most of the time I don't remember until I'm studying this again. What's important is that you understand the ideas. So the first law is the law of conservation of energy. Energy comes out of a system, it goes into the surroundings, or if energy goes into a system, it comes from the surroundings. The second law is entropy is always increasing in the universe, and anything that happens on its own is a result of entropy increasing. There can be pockets of entropy decreasing, like, for example, your body is low in entropy. It's very organized in a certain way. But in order to make that happen, entropy of other things must be increasing. So in your body, for example, you're always metabolizing your food and then breathing out gases, water and carbon dioxide. So entropy is increasing around you to preserve the low entropy of your body. And finally, the third law of thermodynamics was the definition of zero entropy. Perfect crystalline solid, perfectly ordered at 0 Kelvin. So the total entropy, or this is also called a lot of the times the delta S of the universe, it's also called that sometimes, but the total entropy for everything is the change in entropy. The total change in entropy of everything is the entropy change in entropy of the system or whatever we're looking at, and the change in entropy of the surroundings, everything around, everything else, which is the rest of the universe. And the second law of thermodynamics tells us that this must be positive for a spontaneous system. We must have an increase in entropy, total entropy. So when it comes to measuring, what this means is a total entropy greater than 0, change in entropy of the universe, that's a spontaneous reaction. If the total entropy of the universe is decreasing, that is a reaction that won't happen on its own. Okay, it will never happen unless you make you have to make the entropy of the surroundings increase until the total entropy is greater than 0. So if the total entropy is less than 0 for everything, that's not something that happens. And when change in entropy for a reaction is 0, that's a reaction that's at equilibrium. So it's neither spontaneous nor not spontaneous. It's just not doing anything. When it comes to describing or relating here exothermic and endothermic to entropy, this is really important because we think of, as I was saying, a lot of reactions that we think of as spontaneous, they're exothermic, like things that are burning or exploding. Things that happen on their own a lot of times are exothermic. So big question, now that we know that spontaneous reactions are also always those in which the entropy change of the universe is positive, how does exothermic relate to entropy changes? Well, if you have a system like your reaction here and it is exothermic, it is releasing heat, that means that all of the molecules in the surroundings, because they're absorbing this heat, they're increasing in temperature and their entropy is increasing. So what an exothermic reaction means is it means there's an increase in entropy for the surroundings. And so that favors spontaneity for a reaction. If you have an endothermic reaction, that means heat is being absorbed by this reaction. And so for the exothermic reaction, delta H is less than 0, it's negative, it's losing heat. For an endothermic reaction, delta H is positive, it is absorbing heat. But the result is that the surroundings get colder. So an example of an endothermic physical process would be like ice melting. So if you hold a chunk of ice and it's melting, you can feel that your hand is losing heat. The heat is going out of your hand and into the ice to melt it. Thus, since the surroundings of the ice cube are getting colder, the surroundings are becoming lower in entropy. So in an exothermic reaction, the delta H is negative, and the delta S of the surroundings is positive, it is increasing. For a endothermic reaction, the delta H is positive, it's gaining heat, but the delta S of the surroundings is negative. Entropy is decreasing in the surroundings. Okay. So now, remember, to know if a reaction is going to be spontaneous, we have to know about the change in entropy not only for the reaction, but also for the surroundings. Okay. So in terms of the surroundings, the change in entropy of the surroundings is proportional to that. So this means the negative of the delta H. Because, again, if the delta H of the system, the reaction, so here we mean system too. It's not written, but often we don't write system, but we mean delta H of the system. So if the delta H of the system is negative, it is exothermic, then that leads to greater entropy on the surroundings. Okay. And if the delta H is positive, it's endothermic, then the reaction is absorbing heat, so the surroundings are getting colder and their entropy is going down. So these go opposite to one another. They're inversely proportional. But there's something else that affects the delta S as well. And it's because it's that the delta S of the surroundings is inversely proportional to the temperature. This one's go up opposite. These are inversely proportional. Why is that? Well, it's because, let's say, your temperature increase is from 1 Kelvin up to 2 Kelvin. So this is a 100% increase. in temperature. Okay. So at very low temperatures, and that's also, you know, a huge increase in entropy. At lower temperatures, you get a bigger increase in entropy. A 1 Kelvin temperature increase here is a huge increase in the temperature of the substance. Whereas if you're at, let's say, you know, 300 Kelvin and you go up by 1 to 301 Kelvin, that's a small increase. So the lower the temperature is, the greater the impact an increase in temperature will have on the entropy. A 1 Kelvin temperature increase at a very low temperature is a great increase in the entropy of the substance. But a 1 Kelvin increase in temperature when the temperature is already high is a relatively small increase. And so the smaller the temperature that you are currently at in the system, the greater the impact will be on the surroundings. And so if we combine these, the delta S of the surroundings is equal to the negative delta H of the system divided by the temperature. Okay. And so this is going to be how we define the change in entropy of the surroundings relative to the change in enthalpy of the system, of our reaction or whatever we're looking at here. Okay, and this is going to be really important because we know that a spontaneous reaction is going to be one in which the total entropy of the universe is increasing, but measuring the total entropy of the universe, or even the entropy of the surroundings, is very, very difficult. But measuring what's going on in the system is a lot easier. So what we can do is we can measure the delta H of the system. Again, this is the system, even though it's not written. And measuring the system is very easy for us. Our system is our little, you know, box or flask that we're looking at. That's pretty easy to measure. Measuring things about the surroundings is difficult. So we would like to relate the entropy of our surroundings to what's going on in the system. That will help us to measure the total entropy and figure out if the reaction is spontaneous or not. So finally, this leads us to the idea of free energy, or Gibbs free energy. And so again, delta S total, when this is positive, a reaction is spontaneous. And we can measure the delta S of the system pretty easy, but measuring the delta S of the surroundings is quite difficult. So instead, as a substitute, we're going to measure the delta H of the system because that's related to the delta S of the surroundings. So notice here, delta S of the system, we're just going to call this delta S, okay? So anything having to do with the system, we're just going to say, well, that's exactly what we're focused on. And so we'll drop the system here. Delta S of the surroundings, as we just discussed, they're opposite in sign to the delta H and inversely proportional to the temperature. So again, at a low temperature, if you're at a low temperature, putting a little bit of heat is going to raise the temperature significantly and lead to a great increase in the entropy of the surroundings here. Whereas if you're already at a higher temperature, there's a lesser of an impact on the entropy. And so now we're going to plug each of these in to the equation. So we're going to call delta S of the system, we're going to call that just delta S, and that's going to go right here. Then delta S of the surroundings, we're going to call that negative delta H of the system over T. So we're going to put that right there. I'm going to put this right here. And so we get that delta S of total is delta S plus a negative delta H over T. And so now what we're going to do is we're going to multiply both sides by temperature to make this equation look a little nicer. And so we multiply by negative temperature. So we're going to multiply the right side by the negative temperature. And so that's going to cancel the negative here and cancel temperature. We're going to multiply the other side by a negative temperature too. So again, on this side, we're going to be multiplying this out. The negatives are going to cancel here. Temperature is going to cancel. And so here we get negative temperature times delta S. Then we distribute this, here we get just delta H, and then for this term we get negative T times delta S, so minus T delta S. And so that's how we get this equation. And then again, measuring delta S total or delta S surroundings is really hard, but measuring delta H for the system, that's something we can do. Measuring delta S for the system, that's something we can do. And that will get us this quantity T times delta S, or negative T times delta S total. We're going to give this a special name now. We're going to call negative T delta S total the delta G, or the change in the Gibbs free energy of the reaction. And so now if we plug in delta G for minus T delta S, we get delta G equals delta H minus T delta S. And these all now have to do with the system. So we don't have to worry about the surroundings. So when we think about this, so we've gotten this result now. Minus T delta S, we're going to call that delta G, and that is equal to delta H of the system minus T times delta S of the system. So we know that in order for a reaction to be spontaneous, delta S must be positive for a spontaneous reaction. And so if delta G is minus T delta S, that means for a spontaneous reaction, delta G would need to be negative, because a negative times a positive is a negative. So a reaction is spontaneous only if delta S total is positive. So when delta S total is positive, delta G is negative. So if delta G is negative, less than 0, that indicates a spontaneous reaction. If delta G is positive, greater than 0, that is a reaction that is not spontaneous. Delta G equals 0, that is a reaction that is neither spontaneous nor not spontaneous. That is a reaction that is at equilibrium. And so now we can break this down also in terms of based on what delta H is and what delta S is, whether they're negative or positive, we can decide whether delta G is negative or positive, and thus whether the reaction is spontaneous or not. If delta H is negative, an exothermic reaction, and so that favors spontaneity. If delta S is positive, increase in entropy, that also favors spontaneity. If delta H is negative, here, so if delta H is negative and delta S is positive, then you get a negative value for this term, and you get a negative value overall for this term because we are subtracting it. And so that means delta G has to be negative. If delta H is negative and delta S is positive, delta G has to be negative. And so the reaction will be spontaneous. If instead delta H is positive, here delta H is positive, and delta S is negative, that means the first term will be positive and the second term will be a negative times a negative. It will also be positive. So that means delta G will have to be positive. So for a reaction that is endothermic with decreasing entropy, neither of these favor spontaneity. So this reaction will be non-spontaneous. Now, what if we have competing situation here? If delta H is negative and delta S is negative, that means the first term here will be negative, but the second term will be positive. And remember, delta G is not spontaneous if it's positive. So if this reaction is to be spontaneous, the first term, which is negative, will have to be larger than the second term, which is altogether positive, because we have a negative of a negative. And so that will occur if the temperature is low. If the temperature is low, that will make this second positive term small. And so a reaction that is exothermic with decreasing entropy will be spontaneous if the temperature is low, because delta H, this first term, will be bigger than the second term, which is positive. the reaction will not be spontaneous if the second term is bigger, because the second term is positive, the first term is negative. So if temperature is high, the second term will be bigger, and that will cause delta G to be positive. Now the opposite is true for endothermic reaction. For an endothermic reaction where delta H is positive, and if it's increasing in entropy where delta S is positive, that means the second term is going to be the negative term. So if the second term is big, that will cause delta G to be negative, and thus the reaction will be spontaneous. And so here, if T is big at high temperatures, then delta G will be negative, the reaction will be spontaneous. If T is small, then this second term will be small and the positive term will be bigger, and thus delta G will be positive and the reaction will be non-spontaneous. And so that's a little bit of a preview there on the way delta G works. This is a question I love to ask. I love to give you like a situation with delta H and delta S and give you a multiple choice question like this. You can expect that on the final exam for sure. Finally, just note that we haven't been using standards here, right? There is that little standard dot. So if you see standard, remember standard is talking about a very specific state. It is a state where we have 1 atmosphere pressure for all gases and 1 molar concentration for all substances in solution, and a particular temperature like 25 degrees Celsius. So just like delta G equals delta H minus T delta S, for this very specific situation, it's also true. Delta G standard equals delta H minus T delta S, delta H standard minus T delta S standard. Remember, standard is a very specific situation, specifically at 1 atmosphere gas, 1 molar aqueous. So this is a specific version of this. This is the more general version, this is the specific version. Now in your book, they have to give you something, a particular value in the table, so they give you standard values. So when you're using the tables in the table in the book, you're getting standard values. To get a non-standard value of G, there will be an additional calculation that needs to be done, and I'll talk about that next time, what happens when you have other concentrations and pressures. So the standard values can be found in the thermodynamics tables, like Appendix B. And for reactions that occur at temperatures other than 25 degrees Celsius, you can estimate the delta G standard at a different temperature simply by plugging in the temperature right there. So even if you're using standard values, these values do change with temperature, but not that much. And so you can approximate a delta G standard by simply entering the temperature, whatever temperature it is, even if it's not 25 degrees Celsius. But remember, if you have standard values, those are for a very specific situation. 1 atmosphere gas, 1 molar aqueous. And that's as far as I'm going to go in thermodynamics this week. I wanted to use this to talk to you more about the labs. So this is the only lecture that I'm going to give this week. I will give you help with the labs as we go through the week, but your homework is going to be focused this week on reviewing the titrations and the solubility problems. And so I want you to focus on that this week and make sure you really understand that and ask me any questions. I will do one question on the quiz about thermodynamics, and it will be related to this concept right here. Delta G concept. So I do want you to watch this lecture and kind of get a general idea, but I'm not going to do very complicated questions. I'll just tell you right now, I want you to watch this so you have some backgrounds for your experiments this week. I want you to practice stuff from, the chapter 19 still, but I do want you to be able to interpret this right here as we just described. And so I'll give you a problem about that as well. All right.